So we're going to start our number system review. So when we began our number system review, it's all about, it's stupid as it sounds, all the different types of number systems that we have in the mathematical world. It was this picture that we drew, or we had in our notes rather, with all the different types of numbers and how they interconnect within the real number system. So the very central one of this were our natural numbers. The natural numbers were all the counting numbers, 1, 2, 3, dot, 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 all the way up to positive infinity. These were positive whole numbers. The next circle ended up being what's called the whole numbers. And the only difference between the whole numbers and the natural numbers is 0 was included. In the history of numbers, civilizations like the Greeks and the Romans didn't have a concept of 0, so that's why there's a whole nother branch of numbers called the whole numbers. For most purposes, these two systems get lumped together. So we're basically going to say that the natural numbers don't really exist. It's the natural or whole numbers. They're basically the same thing. Right after the whole numbers, we were given the integers. These were positive or negative whole numbers. Just the other side of the spectrum, basically. So we had the -3, -2, -1, 0, 1, 2, 3, continuing on in either direction towards positive or negative infinity. And the biggest group that we had were the rationals. So the rationals was this entire big box. So the rationals included everything that came before it. So the rationals had whole numbers, both positive and negative. And rationals now include any type of fraction, decimals that end, and decimals that repeat. So when you say, hey, I've got an integer, you have a rational. I have a natural number, you have rational. You have a rational, you have a rational. That's when we introduced a brand new type of number. They do not fit within this current scheme. So I'm going to draw them down here. They are the irrationals. So they are not a part of anything that came before it. That's why in the picture they are their own separate box. All the other ones are like nested within themselves. So whole numbers are integers, integers are rationals. All of these are basically the same. So the number 2 can be classified as any one of these systems. Irrational are decimals that never end and never repeat. So when we had our decimals before, they either end or they repeated. Like 3.5, that's a decimal that ends. But 3.3 repeating doesn't end, but it repeats. In this case, the most notable number that's in this group is pi. It is a number that neither repeats nor ends at any point. 3.1415926.5. And you will never have a chance where like, oh, it's the same thing, I could just draw this line over here. You will never have that happen within the number pi. Other things that fit within this group are non perfect roots. Be that square roots, cube roots, fourth roots, whatever it is, you take the root of some number. You're not going to have that. So what we're going to do is we're going to classify and estimate each one of these numbers. Expand my table here a little bit. Oh, I didn't know the numbers were going to expand like that. That's cool. That's exactly what I wanted. All right. So 2/3. I need to estimate that as a decimal. So to estimate it, we're going to do long division. This is 2 divided by 3. So the 2 goes in the house, 3 goes on the outside of the house. Does 3 go into 2? It does not, so we put a 0. We put down the decimal point, add a 0, and now we ask the same question. Wherever we add the decimal point, we add it right above. How many times does 3 go into 20? It goes in 6 times. That's 18. Remainder of 2. Bring down an extra 0. 3 goes into 20 6 times. 3 times 6 is 18. Remainder of 2. Bring down another 0. We will see that this pattern is going to repeat all the way forever. So 2/3 is 0.66 repeating, or even just 0.6 repeating. Both of those are correct. Negative 1.31, we already have it estimated as a decimal, so we're just going to leave it as is. Pi. Well, pi is 3.141592, blah, 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 blah. That's a negative. 3.52, we're already good. Now we're on to the square root of 6. Well, square root, we're going to need a little bit of extra help, so let's actually move on to the next one. We have the square root of 9. Well, square root is just the opposite of squaring a number. So 3 squared, 2 squared, 10 squared, any of those. This one we get 9, we get 4, we get 100. The square root would be the opposite. So instead of squaring, can we move backwards within the list? So I'm going to make a quick square root chart. 1, I squared, it's 1. 2, I squared, is 4. 3 is 9. 4 is 16. 5 is 25. We'll make more if we need to in this chart. So if we look at the square root of 9, that's a perfect root. The answer is 3. But since 6 is not anywhere in this chart, we're going to have to estimate. So the first thing we're going to look for is, where does 6 actually fit in this group of number? Does 6 belong between the 1 and the 4? Does the 6 belong between the 4 and the 9? Does it belong between the 9 and the 16? Or between the 16 and the 25? Should be pretty clear that we want it to be right here. So we draw one number line that starts at 4 and ends at 9. Both of these numbers are perfect. We'll go slang, perf. Because they're perfect, we can draw a second number line that goes between 2 and 3, what the square root of 4 and the square root of 9 are. I'm going to put a few decimal points on here to help me estimate this. So I find 6 to be right about here. To estimate that as a decimal point, it's bigger than 2.25, it's smaller than 2.50, I might say 2.45. So we're going to estimate that one as 2.45. And we're going to have to do it again, but this time with the 11. So I'm going to erase a bunch of this work so we have some room to actually do this. The fact that it's negative doesn't mean anything, just means that our answer is going to be negative when we're done. Move my table over here. Once again, I need to know between what two numbers does 11 fall. It's not between 1 and 4. It's not between 4 and 9. There it is. It's between 9 and 16. So we draw our number line starting at 9, 10, 11, 12. I'm going to try to be as evenly spaced as possible. 16. Our second number line is going to be between 3 and 4. So halfway is 3.5. Halfway between is 3.25. Halfway on this side is 3.75. 11's right here. Straight down, I'm going to estimate this. It's slightly larger than 3.25. Maybe 3.33. Be a decent estimation. So in this case, it's going to be a negative 3.33. We'll then talk about estimating this imperfect fraction. Very similar process. Gotta keep that number. As this one. So we have the 13. It's on the top, so it goes inside the house. 6 goes on the outside. Again, we'll just tack the negative on at the end. 6 goes into 13 2 times. It's 12. The remainder of 1. Then 6 doesn't go into 1. Shouldn't have added the decimal point down here because we don't need to. We add the decimal point up here. Now we asked how many times does 6 go into 10? 1 time. 6. Remainder of 4. Bring down a 40. Goes in 6 times. That's 36. Remainder of 4. Bring down a 0. And now it's going to start repeating. So negative 13.6 is really negative 2.16 with just the 6 repeating. So we've gotten through all of our estimating numbers. It's gotten a little bit busy on this screen. I'm going to erase some of the things that we don't need. And what we're going to do now is we're going to classify these numbers. Which ones are rational and which ones are irrational. So 2/3 or 0.6 repeating. Because it's a decimal that repeats and it's also a fraction, it belongs over here in the rational world. Negative 1.31. That's a decimal that ends. Therefore, it's rational. Negative pi. Well, pi is a decimal that never ends and never repeats. So, negative pi is also a number that never ends, never repeats. 3.52, a decimal that ends, belongs over here. Square root of 6. It's not perfect. Therefore, it's irrational. Square root of 9 is perfect. The answer to it is 3. Since 3 belongs in this group, so does the square root of 9. Negative square root of 11, not perfect, belongs over here. And because negative 13.6 is a fraction, it is rational. So what we're going to do with these numbers now is we're going to place all of them on these number lines. So 2/3, that was 0.6 repeating. Square root of 9 was 3. Square root of 6 was 2.45 is our estimate. This was negative 3.33 as our estimate. This was negative 2.16 repeating. We're going to place them based on their decimal value, but we're going to record them with whatever I have written in black. So I'm going to plot them in light blue, starting with 2/3. 2/3, 0.6. So I haven't even gotten to 1 yet. Here's 0.5. That's 0.75, so it's somewhere in between. 2/3 belongs right about there. Negative 1.31 is negative 1, but then a little bit more. So here's negative 1.25. So it's just a little bit beyond that. Negative 1.31. Negative pi, this light blue is a little bit harder to see. Translation here. Negative pi, so this was 3.14. Much better. So 3.14, but now it's on the negative side, so we have to have at least negative 3. A little bit more, so not quite to 3.25 here. So negative pi belongs here. 3.52, so we have 3. Here's 3.5. Maybe just a little bit beyond that. 3.52. Now that we have estimated our square roots, it's a little bit easier to plot them. 2.45, so we have 2 point, just short of 2.5. Oops. Didn't even follow my own directions. I want it labeled as the original number. So square root of 6, right about there. Square root of 9 is perfectly 3, so it's right here. Perfectly on 3. Square root of negative 11 is roughly negative 3.33, so it's right about here. Negative square root of 11. And then negative 2.16, negative 2, and then it's just about halfway right about here. Negative 13/6.